Learning Outcome 3-4, calculate the Fourier series coefficients of a pure trigonometric signal using Euler's formula. This is going to use Learning Outcome 3-3, which will also be introduced as part of this video. Learning Outcome 3-3 is to determine the fundamental frequency of a sum of trigonometric functions. This learning outcome uses the exponential Fourier series synthesis equation. In your textbook, this is equation 3.38. It's an important equation. You're going to want to have it on your note sheet for tests. This is x of t equals the sum from k equals negative infinity to infinity, a sub k, e to the j k omega 0 t. We'll be explaining what it means and how to use it in the context of trigonometric signals throughout the course of this video. Fourier series only apply to periodic signals. So as a review, a periodic signal is a signal that if you shifted an amount t0 will be the same signals you started with. t0 is your fundamental period. The fundamental frequency in the linear frequency is f. This is 1 over t. Fundamental frequency as an angular frequency is omega. This is 2 pi over t. Again, these are important formulas you want to have on your note sheet. We're going to use Euler's formula to accomplish this learning outcome. You're used to Euler's formula in the form shown here, e to the jx equals cosine of x plus j sine of x. We're going to use it in two other forms, which are mathematically equivalent, but are more useful for this particular purpose. Cosine of x equals e to the jx plus e to the minus jx divided by 2, and sine of x equals e to the jx minus e to the minus jx over 2j. Notice the minus for the sign in between the two exponential terms, and it's divided by 2j and not divided by 2. We want to find a way of writing x of t in the form of this synthesis equation. We're going to introduce how to accomplish this through the course of an example. X of t equals cosine of 2t is the simplest example. The fundamental frequency of our cosine signal is 2. That's this 2 here. It's the only frequency we see, so this is our fundamental frequency. We're going to apply that Euler's formula that we just introduced in the previous slide. But here, our x is 2t. So we substitute in 2t. We can rearrange this just to bring those 1/2 out front, mathematically the same. But now it looks like our synthesis equation. We see the exponential, we see the j, we see the t, this 2 is now going to be our k omega naught. We said omega naught was 2, therefore k is 1. And what's out in front of this exponential is our a sub k. Similar for this next part of the equation, where the 1/2 is our a sub k, and now we have a minus 2, which is our k omega 0. And if omega 0 is 2, then k equals negative 1. So we wind up with an a sub 1 because k is 1, being 1/2, and an a sub negative 1 because k is negative 1, also being 1/2 for this example. All other a sub k are 0. This is important to include this statement because we're looking at writing this x of t in terms of a sub k for k's from negative infinity to positive infinity. We've only written out 2 a sub k's here. All the other a sub k's are 0 in that summation. Now we're going to try a second example. This x of t is cosine of 2t plus 3 sine of 4t. We're looking to find the largest common factor between these two terms, between the 2t and the 4t, really between the 2 and the 4. We're going to still have an omega naught of 2. We want to choose an omega naught such that we get out those two frequencies, the 2 and the 4, where we wind up with a scalar k, and that k has to be an integer scalar between them. If we were to pick an omega naught of 1, then we'd have a k of 2 and a k of 4. Those are both integers, and that's fine. That omega naught is smaller than we need. We can get a bigger one. We could choose an omega naught of 4, but then we'd have to have a k of 1/2 in order to get this first term, and that's not an integer. So we're going to have omega naught is 2. Again, we need to use Euler's formula. We're going to use both the cosine Euler's formula and the sine Euler's formula here. Our sine is scaled by 3, so we scale both sides. We use our Euler forms and write the x of t in terms of those. We again distribute, so we get a sum of complex exponentials, because we're trying to match our synthesis equation. We now need to pair each of those complex exponentials with an a sub k, and therefore we also need to pair it with a k value. For our first term, our k omega 0 is 2, and if omega 0 is 2, then our k value is 1. Our a sub k is 1/2. For our second term, our k times omega 0 is negative 2, so our k is negative 1, and our a sub k is 1/2. For our third term, our k times omega 0 is 4, and our omega 0 is 2, therefore our k is 2. Our fourth term, our k times omega 0 is negative 4, so our k is negative 2. Don't forget that all other a sub k are 0. Your answer is not complete without that. Now let's take that example and add a term to it, minus 5. How do we deal with constants? Well, we can't exactly use Euler's, but we do still have that x of t has to include that negative 5. We do know that that's the same thing as negative 5 times the exponential e to the 0t. Here, our k times omega 0 is 0. That means that our k value is 0. So when we write it into our x of t, we now wind up with an extra term of a0 is negative 5. All other a sub k are 0. We just have one fewer 0 terms. One more example. What happens if we change the frequency of that second term to 7 instead of 4? What is our fundamental frequency now? We need to find the largest value that's common to these terms, where we still wind up with a scale value k that's an integer. Think about it. We're going to wind up with an omega naught of 1. It's the largest common factor between the two of them. What do we wind up with for k values? If omega equals k times omega naught, we're going to wind up with a k value of 2 and a k value of 7. So as we continue on, we now are going to change these 4s into 7s. Same as before. But what's different now is because we have a different value of omega 0, our k values have changed, even though the coefficient values have not changed. If we're going to have omega equals k times omega naught, and omega naught is now 1, in order to get this 2, we have to have a k value of 2. Second term has a k value of negative 2, and now in order to get our 7, we have to have a k value of 7. Next one is a k value of negative 7, and as before, k did not change from 0. All other a sub k are still 0. One more example. Only want to do one term, but I want you to think about what happens when we have an extra constant added in, a phase term. It's no longer having a t, it's just a constant. It's our phase. Omega 0 is still 2, only one frequency present. Still going to use Euler's formula, because it's a cosine. You want to get it in terms of complex exponentials. But now we take everything that was inside of those parentheses, and all of that goes into the exponential. Remember when we have a term with a sum in the exponent, that e to the a plus b is going to be e to the a times e to the b. So there was this sum here. We're going to have to use that property. That's going to expand our terms, e to the j 2t times e to the j pi over 5. Our a1 is now going to be the 1/2 constant out front, and this term here with our phase is also a constant, so that's also part of our a sub k. Remember, if omega naught is 2, our k value is 1. Second term, similar, k value is negative 1, and that complex exponential becomes part of our a sub k together with the 1/2. All other a sub k are still 0.